Okay, last section was kind of meaty. A lot of stuff in section 10.3. The most important thing was becoming familiar with the equations of polar coordinates. We're going to use those equations of polar coordinates to find the areas inside polar curves and arc length as well. As I said earlier, there's a lot of curves where polar coordinates makes your computations much easier. So that's why we're learning it. Especially these curves involving circles, okay? Anyway, so let's talk about the area of a polar region. For the area of a polar region, we're going to use this property from trig. Remember the area of a sector? The area of a circular sector is 1/2 r squared theta. Anyway, so we need to use that. So when you have a polar region, like this is some polar graph r equals f of theta, and you want to find the area from, say, theta equals a to theta equals b of this region here. What we're going to do, I'm not going to do it, I'm just going to mention it. We can divide this up into little pieces. Instead of, like we did in Math 152, these rectangular pieces, right? And then we form the Riemann sum and so on. With polar curves, it's convenient to form these little wedges, these little sectors, and we actually find the area of each sector, just like we found the area of each rectangle, right? And you add up the areas of the sectors, they're each going to have this formula. You form a Riemann sum of the areas of the sectors, you take a limit. You don't have delta x here, you actually have delta theta. Anyway, we'll cover that in class. When you take the limit of the Riemann sum and form an integral, lo and behold, it shouldn't be too surprising that the area of this region, when you take the limit, becomes the integral from theta equals a to theta equal b. So it's basically you're rotating from a to b of 1/2 r squared, where r is this graph of this line here, 1/2 r squared theta d theta b. It's pretty easy. Anyway, so here we go. Let's use that formula and find the area enclosed by one loop of the rows r equals sine 3 theta. Okay, we looked at this briefly last time. Remember, it looks like this. So you want to find the area of that loop, that first loop. The hard part is you need to know when the graph crosses the origin. We talked about it last time. But if you just set sine 3 theta equal to 0, when is the sine of something 0? Well, what's inside the parentheses either has to equal 0, or it has to equal pi, or it has to equal 2 pi, and so on. So then you solve these for theta like you did in Math 142. And you end up, the ones that we're interested in is theta equals 0 or theta equal pi over 3. At theta equals 0, you're here, and then you rotate, and as you get back to pi over 3, you're back to there. So that seemed like a reasonable answer. From 0 to pi over 3 is how long it takes to map that first loop out. So the rest is pretty simple. Since you just had Math 152, you're good at integration. This is what the area of that petal looks like. 1/2 r squared becomes, of course, it becomes sine squared of 3 theta. And you know when you integrate sine squared, you're going to use the reduction formula, or it's actually the half angle formula. Anyway, so the 1/2 factors out, and sine squared of 3 theta becomes 1 minus the cosine of twice this angle. If this is 3 theta, this becomes a 6 theta over 2. So you move the 1/2 out, you get this, and then you can integrate. Now remember, when you integrate 1, you get theta. But when you integrate cosine of 6 theta, don't you need du? Du would be 6. So if you want to put a 6 in there, you'd have to put a 1/6 out front. So that's where that 1/6 comes from. That comes from compensating for the du. And the integral of cosine is sine. Anyway, so this is what you get. And then when you evaluate it between 0 and pi over 3, you end up with pi over 12. Isn't that cool? So if you wanted to find the area of the entire rows, it would be 3 of those, right? So it'd be 3 pi over 12 or pi over 4. Nice. I knew you would like this. As long as you feel comfortable with these equations, it's not too bad. Find the area enclosed inside the circle. Okay, r equal cosine theta. Remember, that's a circle that's along the x-axis with radius 1. And this sure enough is a cardioid. As long as a is greater than or equal to b, You know it's a cardioid. So it's, and so then anyway, you can use your calculator on this. So this is what you have. You have a cardioid here, and you have a circle. And since this is a minus, the cardioid, notice, see how it's been flipped across the y-axis. So if it's inside inside the circle, outside the cardioid, and if you can see it, it's this just shaded region. So what I'm going to do, I'm going to use symmetry here. I'm going to look at twice this region in the first quadrant, okay? And I know it's from 0. I got to figure out where they cross. If I can find this area in the first quadrant, then I can multiply it by 2 to get this one down here in the fourth quadrant. I need to find out where they cross, and furthermore, what you have is, notice you're going to have a difference between two functions. So just like in Math 152, if you want to find the area between two curves, it's going to be the outer areas minus the inner area. So you end up with 1/2 r outer squared minus 1/2 r inner squared. That's how you would get the area of the region that's between two curves. Now, where do they cross? Well, you would set the cosine of theta equal to 1 minus cosine of theta, and you end up with this, and so that would be where cosine theta is 1/2, so that's at pi over 3. So if I go from 0 to pi over 3 and multiply by 2, the outer function would be the circle, right? So you got, no, oh, by the way, the 1/2s cancel with this 2. 2 is for the symmetry, the 1/2 is from the formula for the area. So the outer function is cosine theta. You get a cosine squared here. The inner function is this. So you get 1 minus cosine theta squared. And the rest is just your integration techniques. When you multiply this out, I believe, don't the cosine squares cancel? You can hit the pause button if I'm going too fast here. You end up with integrating this. And so it isn't hard to integrate. I get 3 radical 3 minus pi all over 3. Nice, huh? A couple more. Find the area inside the inner loop of the limacon. R equals 1 minus 2 sine theta. It's a limacon because A is less than B. So sure enough, it looks kind of like this. This is your graph. So what you need to do, the hard part, is knowing where the limacon is 0. So if you set it equal to 0, where R is 0, you get sine theta is 1/2. And the ones that I'm interested in are between pi over 6 and 5 pi over 6. Let's see if you can follow this. So at 0, your R is positive, but somewhere right around here is where the R value is 0. That's at pi over 6. Now the R value is going to be negative from here all the way back over to here somewhere in the second quadrant, right about there. And that's going to be your 5 pi over 6. So between pi over 6 and 5 pi over 6 is when you have that inner loop. The rest isn't too bad. The rest, you're between pi over 6 and 5 pi over 6, 1/2 r squared. You don't have to worry about outer and inner here because there is no inner. The inner is just 0, right? So when you multiply this out, the integration is a little messy. I'll let you check me on this. You can hit the pause button and see how this works. But multiply it out. I had to use the reduction formula here, and I believe, yeah, that's how you do it. And then you'd integrate. When you integrate this, you have to have a 1/2 for du. I should say you have to have a 2 next to the cosine 2 theta. So you have to have a 1/2 outside, and that's why this 2 goes away, because you had to have a 1/2 out there. Anyway, this is your answer. That's what I get. 2 pi plus 3 radical 3 over 2. Okay, isn't this fun? I knew you would like this. It is fun. All right, a couple more things. Find the area inside the rows R equals 2 cosine 2 theta. So you're going to have 4 loops, right? Four petals because it's even, right? Oh, and outside the circle. Oh, okay. I see. It looks like that. Okay. So it's the area inside the rows and outside the circle. So I gave you a little piece of it. I'm going to use a symmetric argument. I'm going to find that area and then multiply it by 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So if I can just find that area, multiply it by 8. I need to know when the rows hits the circle. And I got that if you have 2 cosine 2 theta equals 1, cosine 2 theta is 1/2. If you solve that for theta, I get 2 theta is pi over 3, right? That's where the cosine is 1/2. And so theta would be pi over 6, which seems like a reasonable answer. So my integral gets set up like this. This is how I set up my integral. I'm going to go 8 times the area, the integral from 0 to pi over 6. That's going to give me that upper half of that pedal of outer minus inner, outer squared minus inner, inner squared. 2 cosine 2 theta squared minus 1 squared. Anyway, like I said, the rest, the hard part is probably the stuff from Math 152. Isn't this Math 152 type stuff? Multiply it out carefully and combine. Use the reduction formula here. And then I'll let you hit the pause button and check me on this, but I end up with 4 times the quantity pi plus 3 radical 3. All right, let's talk about arc length for a second. The way you find the arc length is go back in polar coordinates is do what we did with the same idea to find the slope of the tangent line in polar coordinates in the last video. Didn't we actually look at the conversion factors between polar and Cartesian coordinates? And you could think of these as parametric equations involving theta instead of t. So then what you could do is you could use the arc length formula we talked about in section 10.2. Instead of dx dt and dy dt, think of this as dx d theta and dy d theta. All right. Anyway, there's a lot of steps in between here that I'll let you fill in. But if you take x, which is right here, and you differentiate with respect to theta, remember we talked about this. You're going to have to use the product rule when you find dx d theta here, and you're going to have to use the product rule here. So if you use the product rule to find dx d theta here and dy d theta here and plug them into this and simplify it, a lot of stuff cancels. You end up with this. So this is the same thing as this. I just found dx d theta and found dy d theta, plugged them into here and simplified them. I got this. This is the formula for the arc length in polar coordinates. Okay, so let's look at an example. If you recall, arc lengths can be kind of difficult to compute the exact value because we have a square root involved, right? This one is kind of rigged. I think it comes out nice. So here's the formula. The arc length is the integral from a to b of square root of r squared plus dr d theta squared d theta. So it looks like this. What is dr d theta? Remember that the rule for differentiating 2 to the x is it's ln of 2 times 2 to the x. So dr d theta would be ln of 2 times 2 to the theta. So that's what you put in, right? You put this in for dr d theta, and you square it. You get ln of 2 squared times 2 to the 2 theta. What is r squared? When you square this, you get 2 to the 2 theta. But look what happens. You can factor out the 2 to the 2 theta out of the square root, because isn't this just 2 to the theta squared? So you factor out the 2 to the 2 theta, take it out, it becomes this. So this is just the integral of 2 to the 2 theta, which isn't too bad. The integral of 2 to the x would just be 1 over ln of 2 times 2 to the x. So anyway, this is easy to integrate. This is a constant. This gets factored out. The integral of 2 to the theta is 1 over ln of 2, 2 to the theta. And so when you plug in 0 to 2 pi, you get this. And this is what it looks like, by the way. It's kind of an interesting graph. It's a spiral. So you're looking at the length of this part of the spiral. Amazing. Okay, well, I've got a little bit of time left. So here's a summary of everything we've looked at in this chapter. Not a summary of everything. Why did I say that? Hey, here are just some things I stuck in here. Some things that are important would be the conversion factors between polar and Cartesian coordinate system. The picture helps a lot, doesn't it? So and also this is kind of a summary, I guess. These are the formulas that you should know. For the slope of the tangent line dy dx, in parametric it's dy dt over dx dt, and it's the same thing in polar, except that we're thinking of the parameter as being theta. Remember, we're thinking of these as parametric equations, right? For the area under a curve, parametric, if y equals g of t and x equals f of t, it just becomes this. In polar, it becomes this. And for the arc length, this is the arc length in x and y. In parametric, it becomes this. In polar, if you just replace these for x and y and plug them in here, it becomes this. Okay, so those are the formulas we're going to use. Alrighty, we'll see you next time. Bye-bye.